Well, hello again everybody. Now before we start this video I thought it would be useful just to deal with some housekeeping from the last video, because I was trying to explain how to decode the serial protocol in my usual dog's dinner kind of fashion, and I don't think I made a particularly good job of explaining it, and I think I also made some mistakes. So very quickly I'm just going to go over it again. So we have these serial data streams, and what we had on the screen before, on the oscilloscope screen, we had this. And really what I should have explained is normally the waveform that we're looking at, it sits at this high level, because that would be, that's 5 volts, if I just scribble that in there. And that's called a high idle state. So when we're not sending any data, the actual pin we were monitoring would be sat at 5 volts, and that's called a high idle state. Now the first thing that happens when you send a serial data packet is that you have what they call a start bit, and a start bit is basically, it pulls down for 1 bit length, which was I think we decided, didn't we? We measured it for the 9600 board that we determined. It was approximately 104 microseconds. So the start of the data packet is defined by pulling low for this 1 bit time, and then the data starts. And the way that they arrange the data is they quite often use this term LSB and MSB, and all the radio people know we're not talking about sidebands and things. We're talking about least significant bit and then the most significant bit. So it's binary, so it starts here on the left and it works its way to the right. So our first bit position, which for some reason they never call it bit 1, they always call it 0. So our 0 bit is worth a value of 1 because it's binary. Our 1 bit is worth 2. Our 2 bit is worth 4, our 3 bit is worth 8, and then add it up, 16, 32, 64, 1 to 8. So that's basically the way it works. And I think one thing that I did was, I also, when I actually wrote these down, I don't know why I did it, I wrote the 0, 2 rather than 2, 0, but that was wrong. It should be 2, 0, so there's our 2 there, and then we've got 0, 0, 0, 0, and then we've got the signal goes high because it's a high stop bit for this. So have I made it better or made it worse? I don't know, you tell me. That's my go at serial decoding. So last time we were having a look at the data that was going into the 485 transceiver chip, which is, where's it gone? Which is that chip down there. And we were looking at that on the oscilloscope, and we did some manual conversion of the data, and we also used the automatic decoding function on the oscilloscope. But I don't know about you, I wasn't completely satisfied whether or not we'd actually done the conversion correctly. So going through the drawers at work, I thought I had one of these 485 converters. So this is actually looking at the differential pair 485 signals, which is coming out of the alarm panel, and we're going into this 485 converter, and it's actually converting it into a USB here, but it's running one of those FTDI chips, which is basically USB to serial interface. So to cut a long story short, what that allows me to do is to connect the 485 signal coming from the alarm via this interface. We can connect it into a computer. Now the picture that I've got here at the moment, you can see that okay, that's just an extract from last week's video, and you can see that one of the packets that we decoded was 02, 03, 04 and 07, and that corresponds to this data here. Now in the background we've got the what they call the Bray terminal device running, and the Bray terminal is just a free interface that allows you to inspect data received on a serial port. You can inspect it and record it, and you can view it in various different forms, hex and ASCII and other formats, and you can timestamp it. So if you're into doing serial data recovery or looking at any kind of device that uses a serial data stream, it's really good and it's free. But this data here that we can see just being printed up on the screen, that's live information that's coming in from our alarm system at the moment via the 485 interface, and just picking out there, we can see we've got the numbers 02, 03, 04 and 07, and that exactly coincides with what we recorded. So I think that's a good test really. It shows that we did it correctly. And just to prove that I'm not making it up, we'll just unplug the alarm system, and in theory the data should stop. So unplug it now, and there we go. Let's plug it back in again and see if it restarts. It does actually take a few seconds to boot up when it restarts, so let's just see how long it takes. I've plugged it back in. Are you going to restart? Please restart. Come on, what are you doing? There we go, and it's restarted. Now I realise I haven't given a particularly in-depth discussion about 485, but all you really need to know is that it's very similar to RS-232. But the problem with RS-232, it can only go, you know, a few tens of feet, and it's designed for connecting computers together locally. But the 485 network has the great advantage that it will go up to 4,000 feet. And it's a multi-drop network, which means that you can hang lots of devices all off the same twisted pair network. And the twisted pair is nothing special. Literally all you need is two pieces of wire. You twist them together, and there you go. That's your twisted pair network. Now, if you want to transmit and receive in what they call half duplex, which means that you transmit and then you wait to receive something, you can't transmit and receive at the same time. So if you transmit and then receive, that's half duplex. You only need two wires, two twisted pairs. But if you want to do what they call full duplex, which some systems do use, you actually need two twisted pairs. You need a dedicated twisted pair for transmitting and a dedicated twisted pair for receiving. And the advantage for that is that you can transmit and receive at the same time, which can be faster. And some applications you need to do that. But again, twisted pairs go up to 4,000 feet, multi-drop, quite good. The signals that go down it are what they call differential drive. So rather than just switching the power on and off to it, what they actually do is swap the power over. So perhaps the easiest way of explaining that is what you could do is, you could, if you wanted to, imagine you had a light at the other end of this wire. What you could do to send a signal, you could put a battery on like that, and the lamp would come on. But what a differential system does is, for part of the signal, it will put the battery on that way, and then effectively it turns it around and puts it on that way. So basically it crosses the polarity, it swaps it, and the advantage of that is you get much better noise immunity. I've got the red wire and the black wire here, and we've got that clipped onto the scope probe, and I was looking at the data and I've just frozen the screen on the scope, so I'll just show you that, and you're going to be able to see what's on these two wires, and you're going to see that they're opposite to each other. Now apologies if the camera's shaking a little bit because I'm having to hold it by hand here. Yeah, it is going to shake, isn't it? So basically you can see the signal on our red wire is in yellow here, and our black wire, I'm afraid, it's in green. But if we actually just superimpose one signal over the top of each other, you can see that the signals are equal and opposite. So they're different, they're differential. Well, I'm not sure if you remember last week we were also talking about the electric climbing telephone monkeys. Well, apparently some people call that the Strowger step-by-step system, which seems rather complicated to me, so let's just stick with electric climbing monkeys. And the other thing that I was talking about last week was this DTMF chip, which is actually designed to decode dial tones, and it provides a 4-bit output code depending on the dial tone it receives. So it's designed so that you can actually control the alarm system remotely through a telephone system and using one of these handheld tone dialers. I think these tone dialers are built into telephones and your mobile phone these days. But one of the things that I thought was odd at the time was it had this 3.5795 megahertz crystal, and one of my subscribers, Jarrett does stuff, he's got a channel of his own, he was just speculating that it was It was a typical NTSC colour burst crystal, and maybe just speculating that there was just thousands and thousands of these available at low cost, and that's why they did it. So I just thought I'd mention that because I thought it was just an interesting idea. Now, one of the other comments that we had was from Average Joe, who just pointed out that what the correct name for these two switches are, and he just pointed out that these are what they call these in the alarm business is they just call them anti-tamper switches. So this switch on the front panel, it actually operates a plunger which presses on the back of the alarm system. It actually presses against the wall where the alarm system's installed. So if you actually just pull the alarm system off the wall, it would release that spring which would open the micro switch, and that would set the alarm off. And there was this other anti-tamper switch here, which is well, this one actually detects if you actually remove the back cover from the alarm. So yeah, two anti-tamper switches, so thanks for that, Joe. Well, come Thursday, my tolerance level for all things annoying has just gone. So yeah, I've had enough. I'm going to unsolder this bleeper. It's driving me nuts. Silence is golden. I think that we mentioned at the very start of this video that this alarm panel kind of had two parts to it. It's got the main microprocessor board here, where all the all the microcontrollers and all the programmability is, and the RF transceiver. But it's also got this little daughter board which plugs in on a ribbon cable. He said. Here we go. So this is the incoming power supply, and it's a 4-core cable, and they've actually just separated it into two pairs. So I guess they didn't think there'd be enough current carrying capacity in a single core, so they've just twisted the red and the black together to make one core, and the yellow and the blue to make another. So I guess, being typical contractors, they just used whatever they had in the back of the van. And then we've got a couple of connections that say Bell on them, two pairs. So I'm guessing they're going to the exterior bell box that you have on the outside of your house. We've then got what they call a bus connector here, which I'm thinking is this is where we were connecting the 485 to previously. I just soldered a couple of wires onto it. In fact, well, maybe we can see that. So we've got a connector that says bus here, but there's also a bus connection on these 4 screw terminals. So do those try? Oh yeah, okay. So it looks like you can plug in that 485 network. You can either plug it in on this little 4-way header, or you can equally well just wire to this connector block here, because you can see that the wires are coming from the 4-way header going to the terminal strip above. These are the two telephone connectors where it's got a line in and a set connection. So one of these is actually designed to go to the connector on your wall box, and I'm guessing the other one is to plug into a handset. I don't know, what do you call them? Telephone connectors. I used to know what the name was, but I've forgotten. We've got a power socket here, which so it looks as though you can either plug your power supply into this little power socket, or you can plug it into these connectors at the end. And we have got a 5-volt regulator and some smoothing capacitors. So you can see we've got all these little blue things here, and what they call them is metal oxide varistors, and it's actually printed on the board MOV for short. Now what they are is a type of resistor which is voltage dependent. If you put a low voltage across them, the resistance will be very high, but if you put a high voltage across them, the resistance drops, and it drops very sharply at what they call the threshold voltage. What these are for is to protect against high voltage transients. So if you've got all long lengths of wire here running all around your house, and then maybe you've got a lightning strike nearby, you'll get quite a high voltage induced in all the cabling. And that high voltage will run down the wires and it'll get onto your alarm board here. And potentially, because some of these connections are going up to things like microprocessors, they're very, very sensitive to voltage spikes, and you can blow them up. So what the purpose of these MOVs is, if you get a high voltage spike coming in, the resistance of these drops, and effectively they short out the high voltage spike, and they dissipate the energy within the high speed transient. They actually dissipate that as heat. Now, depending on the size of these, they can dissipate various amounts of energy. So you'll see that some circuits have little tiny MOVs in them, and some circuits have much bigger ones. Now, I'm hoping you can see along this board, and I will bring you in a bit closer in a second. We've got these little V's. Let me just see if I can bring you in. You can see that each one of the input terminals here has got these little V's across them. Twin V's, and there are little arrows pointing towards each other, a gap in between them. And these are another form of circuit protection. They're what they call spark gaps. And yeah, I don't know if everybody will be familiar with these. You quite often find stuff like this on radio equipment, and also telephony equipment. Yeah, I lent my teeth to the horse today. So again, anything that's got long wires connected to it, you can get very high voltages induced in them, and you don't want that high voltage doing any damage to the rest of your circuit. So basically what these little spark gaps do, if you get a high voltage, the high voltage will jump from the terminal and it'll jump to the other side, from one side of the V to the other, and again that will actually allow the voltage spike, the little flash, it'll allow it to get to ground rather than going around the rest of your circuit and doing some damage. And you can see that every one of these input terminals here has got these little spark gaps on them. And yeah, I find that quite interesting. I mean, I've done a little bit of electronics design in the past, and even done things with field wiring on them, and I've never really considered putting spark gaps on them, and I'm wondering if it's something I should be considering in future, because it doesn't cost anything. It's not even a component, it's just printed onto the PCB, and all you do is just remove a little bit of the solder mask, or you don't print the solder mask around the V shape on the printed circuit board. So I think that's really interesting. And we've got some pretty big diodes here, and I'm guessing that some of these diodes are forming the bridge rectifier circuit, because this will take an AC supply. But there's some other big power diodes, and again, I'm not exactly sure what they're for. We've got some capacitors here, which I'm sure are to do with, again, the AC smoothing before we get into this 5-volt regulator here. There's our ribbon cable connector that connects all these various inputs and outputs to our main circuit board. And we've got 2 relays here, and so you can obviously program these relays. I think you can program the alarm to do things like switch lights on and off, or maybe switch on another sounder. Now, I've just seen something else that I've never noticed before. You can see that these little red dots here in various locations. At first I thought they was some kind of components, but they're not actually connected to the pads. And looking at some of the other components on here, I can see the red dots just sticking out from underneath them. So I'm guessing this just must be some kind of assembly glue that's used to hold on the components. Maybe it's because there's a mixture of through-hole components and surface mount that they've done it that way. But yeah, I know that quite often when you're putting components through, I wonder if it's gone through a flow solderer. A couple of other little things on here which I'll just point out. You see there's a brown thing here, brown stroke cream colour, another brown one there. They look a bit like capacitors. In fact, they also look a lot like these MOVs. But what these are electronic fuses which automatically reset. So if you've got a fault on the circuit and it's drawing too much current, rather than just blowing a fuse, what these do is they're kind of a thermal device, and they heat up inside and they disconnect the circuit, and then when the fault clears they automatically reset. So we've got a couple of them, and I guess that's much easier than wiring up fuses and having to replace them, because I'm assuming that this thing can well, this looks as though it's in circuit with the positive and negative for the bell, and I'm guessing that if you just let the typical alarm installer wire these things up, they probably have a habit of shorting things out, and you don't want to be blowing fuses up or blowing up output transistors. So these are automatic electronic resettable fuses. That's what they're in there for. So I think that's quite interesting as well.